Thank you for the introduction. Yes, I'm not Greg. Greg couldn't make it today, so I'm going to give the presentation for him. So this talk is very much along the lines of what Mark's first example was. So Greg's a deep learning reconstruction expert, and we've been working together on this project. So basically, I gave him all my tools for breast CT simulation. And so he's been developing CNN-based reconstruction for like sparse view, noisy CT data. So here you just sort of have a overview of CNN-based image reconstruction where you put in a noisy FBP image and you hope that the neural network is going to be able to estimate the true image. And by the way, since all my stuff is simulation based, we know the ground truth exactly. And so here's just an example reconstruction. You can see it's pretty close. All right, so the point is, just like what Mark said this morning, is that most neural networks are using a mean square error type loss function, right? Oh yeah, just here's some examples of the training data set. So in a similar theme to the other talks in this session, let's focus on like small details in the image reconstruction. So what we did after the initial development of the reconstruction algorithm, we put in this small contrast detail insert right here, which roughly models like an array of microcalcifications. All right. So what happens to those when you run this through the network? All right, so here's the truth, here's the input, which is it's pretty crappy looking, but then you run it through the network and it's it's much better than the input for sure, but you also see you've wiped out many of the signals there in the contrast detail insert. So what we want to do is see if we can do better than that. All right, and so I just want to also point out that this mean square error issue is not just something that's an issue for neural network image reconstruction. We've also done the same thing with total variation based image reconstruction. So here I have the ground truth image and then two images that were generated by total variation minimization with two sets of different parameters. All right, so on the bottom, you see the root mean square error for each of those reconstructed images, but then you also can visually see the contrast detail phantom, and you can see the reconstructed image with lower RMSE has many more of those signals wiped out than the one with the larger one. All right, so the pitfalls of MSE, just like echoing Mark's point. All right, so the one thing that Greg came up with is he came up with something called the observer reg, which I'm not going to get into the details of what that is, but basically the point of it, it's a term that will preserve the visibility of those small signals. All right. So you just add this onto the least squares thing and you do your training, and there's a tunable parameter also. Okay, so this is the part of the key point of this talk is understanding that there's this lambda here that you can tune. And here's like a series of images that you see for different values of lambda. So all the way on the left, that's if you're not doing this at all. So this is the mean square error image. You can see the signals are wiped out. And as you go to the right, those signals come back, but then you also are paying a little bit of a price because the images are noisier. All right. So really the main point of this talk is like, how do we determine this lambda? All right. So we're going to do that also on a task-based method. So Mark already talked a little bit about signal detection, so I'll try to breeze through this quickly. So for signal detection, one way to understand the metric is to think of a two alternative forced choice experiment. So you're given a signal there on the top image, and you're shown two images, one with the signal present and one with the signal absent. All right, and then as an observer, you have to say which one it is. It's on the left or on the right. All right. And the valuation or the number that you report for this 2AFC experiment is the percent correct. Okay. So if you get 50% correct, that means you're just guessing. So that's really bad. All right. 100% correct's the best. All right. And so the percent correct is actually the same thing as AUC under the R of the area under the ROC curve. All right. Okay. So for image reconstruction, how do we use this? So we're actually going to be measuring the efficiency on the signal detection task. So there'll be an inherent AUC in the data space, and the image, when you go through the image reconstruction and show images, the AUC will always be equal to or less than that value. You can never improve signal detection. And so the efficiency is like how much is measuring how much do you preserve of the AUC. All right. All right, so then there's two concepts that Mark pointed out. There's the ideal observer and then the human observer. Obviously, the ideal observer is probably going to do better than the human observer. But so the ideal observer is basically telling you what's the maximum that you're going to be able to get out of it. And so both of them I find are kind of useful. But the main thing for this talk is developing the human observer thing, because the ideal observer we've done previously. So in order to set up this thing, we need to specify what our detection task is for the breast model. So we're come back to the breast phantom. We're using a fixed background, the one shown on the upper left. And then we insert a signal right in the middle, okay? We add noise to the level so that the data domain AUC is not perfect. It has to be a little bit less than 1, otherwise you can't get a useful measurement for the efficiency. All right, and so for all of the images I'm going to show, the AUC in the data domain is 0.866. All right, so then our ideal observer development was done and shown in this paper, and actually this was collaborative work with Mark, where he ran several neural network-based observers, and we developed a channelized hoteling observer, and we found that they all agree very well on the total variation image reconstruction. So we just, for that particular observer, we stick with the channelized hoteling observer because it's a little bit more lightweight. All right, so now applying that observer, the ideal observer, to this evaluating this new neural network-based image reconstruction, we got these results. So remember, lambda is tuning this observer regularization on the x-axis. So the higher lambda is, the more we're sensitive to small signals. And in fact, that's what you see. So as you turn lambda up, then the ideal observer detectability also goes up. All right. And so that's sort of that sort of agrees a little bit with the visualization. You can see that the signals are kind of wiped out here on the left and they're coming back on the right. Okay, so the criticism of the ideal observer in this particular case is that it doesn't tell you when to stop, right? So if you're just going by the ideal observer, you just keep turning up lambda, so that's not very good. Because in fact, the least that you process the data, the better it is for the ideal observer. And so there's a gap there with the human observer. So what we're going to try to do is develop a simple human observer. So what we're going to propose to do is just to use a signal-Laplacian for our observer template, okay? And so to motivate this, I'm just showing a very simple example of a signal in a independent Gaussian noise field. So the signal's up there on the upper left. And in this particular case, the ideal observer is the same thing as using a signal as a hoteling template of the signal itself. That's the image on the left. And then this new template thing is just that we're proposing for human model observers on the right is a signal-Laplacian. All right, so this is not a completely new idea, by the way. There's people know that humans are sensitive to edges of things, and so that's what's motivating this. the thing here is that we wanted a kind of simple model. So we're not doing the full channelized human model thing. We just have one single template, the signal-Laplacian template. All right, so now the question coming back to the Gaussian noise field. So the variable here for the imaging is just doing different levels of blurring, all right? So at the top, we're adding noise and we're not smoothing the image at all. And you can't really see, oh yeah, the images, come back. So the images on the left here have the signal in it. The images on the right don't, okay? And I'm increasing the blurring as I go down. All right, so you can't see anything on the left there, or at least I can't. I don't know, maybe you guys can see something there, but when you come down here and do a little bit of smoothing, you can sort of tell that there's this white spot in the middle of the image. That's the signal, especially when you compare it to the signal absent, you can clearly see it. And you can still see it when you go to further smoothing. All right, so let's look at well, okay, SNR is related to AUC, but let's look at the metrics for both using the pure signal, which would be the ideal observer, versus the signal-Laplacian, which is this thing on the left. So the pure signal is the blue curve, and the proposed signal-Laplacian is the red curve. And you can see that the ideal observer is telling you not to do blurring. In other words, use the image at the top row, all right? But the signal-Laplacian is not saying that one's not the best one. Instead, we should do a little bit of blurring. So this is just to motivate the observer, and it sort of agrees with what you see here, or at least I think it does. All right, so now let's try this back on our CNN image reconstruction. So here what I'm showing is in the blue curve is the previous ideal observer. The orange curve is just using the signal as our hoteling template, and the green curve is using the signal-Laplacian. And you can see that using the signal-Laplacian actually gives you a peak at a value of lambda. It doesn't tell you to keep increasing the lambda. So this is an encouraging piece of evidence that maybe this is useful for human observer performance. And just to see the visual of it, basically we come back to the same breast CT image, and here's a series of reconstructed images at different values of lambda, and the one that maximizes that signal-Laplacian AUC is this one. And so you can, to me, it's a reasonable balance between noise and being able to see those signals in the insert. All right, so this is my last slide. So basically, yeah, just showing you preliminary results for this using the signal-Laplacian to tune image reconstruction parameters, but we obviously need to do more work and do like reader studies to see if this is actually can be used as a surrogate for human performance. So thank you for your attention.
Okay, the talk is open for questions.
Yeah, that's very interesting work here. So you probably mentioned, can you tell a little bit what's the motivation not doing channelized hoteling observer? And
oh yeah, I skipped right over that. Yeah, I didn't say anything about that. So yeah, to evaluate the observers, we need to do realizations and a lot of noise realizations. And so the more, like if you do a channelized observer, the more channels you have, the more realizations you need to have a good covariance estimate. And so basically we were just trying to come up with the most lightweight model possible. So, I mean, I think it would be a valid thing to do. It's to like do a channelized hoteling observer with like, some of the channels that are known to be good for human performance.
For the signal-Laplacian, How many realization? I didn't catch. How many realization do you need? For
Oh,
that?
yeah, so that's, we haven't really explored that dimension, so we just overkilled, so we did 1,000 realizations.
But you
but
think it will be less than
It'll
channel
it
hopper?
definitely
Okay,
be less
gotcha.
than that, yeah.
One last question, quick.
sure.
So this is for the classification. So that's
Mm.
very sharp, small object. You look at it, make perfect sense. What about low contrast lesions?
Right, it's definitely something, I mean, this is actually one of the motivations for this using the signal-Laplacian, because actually if you use the signal-Laplacian as your template, that's equivalent to doing a single channel Hotelling observer where the channel is the gradient of the signal. And so that's exactly the situation that I was thinking of when you're trying to model detectability of a large signal, because when you look at a large signal, it's sort of hard to pick it out from the middle of the signal. You're actually looking for the edge, right?
Okay.
And so then, yeah, so
I'm going to push back just a little bit on that. But if you look
Okay.
at edge, small, larger, different sizes, the Laplacian signal probably looks similar. However, we know that a much larger object will be much easier to detect if we assume the same contrast in a small object.
well, okay, why do you say that?
Right, just like common sense. If I have a say 500 unit contrast, very challenging.
Right,
If it's 1 millimeter, I have a hard time to look at.
right.
If I have a 10 centimeter, even just a same contrast 500 unit, I have no problem seeing it at all.
Okay, no, you're talking about like really small compared to different sizes, but I think
Right.
once you get to a certain radius, it's going to be about the same, you know.
Okay.
I don't know.
All right.
All right.
Thanks.
Anyway.
Yeah, well, part of my question was about the signal size variation, but the other question is, what about the background structure that you?
Okay. Yes. Very good. Yeah. So this is just yeah, we haven't actually gotten into that yet. So far, we're just looking at fixed backgrounds and noisy fields. But yes, it's a very important issue.
Just one quick question, like, did you compare the Laplacian model observer with the very common used like non-pre-widening eye filter? So
Right. Yeah, that's okay. No, we haven't like so that's, I guess that's another thing that I should have put in the summary slide is, yeah, we need to compare with other observers, but you got to remember our purpose here is to tune parameters for image reconstruction. And so you know, performing reconstruction after reconstruction can be really time consuming. So we might be actually skimping on the side of a good modeling of human observers, you know, but it's something that's sort of in the ballpark that, you know, can be readily computed, that you can compute, you know, that's so you don't spend all your time computing the model observer, and instead you can focus on trying to map out the parameters of the image reconstruction. Yeah, but it's a good point. Yeah.
So thank you for the interesting talk. I'm wondering, when you have this extra term in the loss function,
Yeah.
did you observe if the algorithm would introduce structures that you're trying to detect?
Oh yeah, that's an excellent point. And in fact, it pretty much, yeah, we can look at your question right here. So there's definitely like some spots in there, you know, that don't belong to the contrast detail phantom. But yes, also brings up another interesting point is like, can you somehow penalize that, right? And so then one of the things we want to look at is signal variability and background variability, because you know, that what we're doing right now is we know that for all the observers are signal known exactly, background known exactly. So we're hoping that will address that issue.
Thank you.
Yeah, sure.
okay, no more question. Let's thank speaker again.